In this video, we're going to discuss an important theorem in mathematics, or in calculus in particular, called the mean value theorem. It's an application of continuity and differentiability. It uses the intermediate value theorem, and a more specific version of it is where we're going to start, and this is called Rolle's theorem. Okay, so what Rolle's theorem says is if a and b are any real numbers, okay, and let's just take a less than b, and you have a function f of x that's continuous on the closed interval from a to b, so that means it's continuous also at a and b, and it's differentiable on the open interval, so it might not be differentiable at a and or at b, but everywhere in between it's differentiable, and the y values at a and b are the same. Okay, so I know that's a lot of conditions that you need to remember. So I'm going to draw you a picture after. But if all of those are satisfied, then there is at least one value c that's between a and b, such that the derivative at c is equal to 0. Okay, so let me try and draw you a picture of what's going on. So if I have a function, so let's say here's a, here's b. Okay, now they're the same value. Okay, so here I have f of a and also f of b. Okay, they're the same. And you have a nice smooth function. Okay, so maybe the function does something like this. Okay, so it's continuous and differentiable. What Rolle's theorem says is that there is a point C, here it looks like it's in the middle, where the tangent line is horizontal, or the slope is 0. Okay, so because you have to start and finish at the same place, and it's a smooth, nice curve, there has to be at least one point where the derivative is 0. Okay, now there could be many points. The theorem guarantees that there's at least one. Okay, so maybe I have it up here. And maybe it does something like this. Okay, still we have that f of a and f of b are the same y value. Okay, now here we have a bunch of c's, okay, with derivative 0. So all three, I'm going to call this C1, C2, and C3. We actually have 3 here that have slopes of 0. So derivative of 0. So the theorem guarantees 1, but there could be more. But you have to have a bunch of conditions. Okay, so the first one is that it's continuous on the closed interval, okay, from a to b. It's differentiable on the open interval from a to b. So continuous means there's no jumps, no asymptotes, no holes in the interval. Differentiable means that you're continuous, but there's no sharp turns, there's no vertical tangent lines. Okay, and then the last thing you need is that f of a and f of b are actually the same. So the y values are the same. So you have these 3 conditions. If they're all satisfied, then you get this special c value. Now, it does not tell you how to find it, just that it exists. Okay, now notice if you don't have differentiability, so I'm going to write here, not differentiable on the open interval, then you could have something that looks like that. Okay, so here's A, here's B, it's continuous everywhere. F of A and F of B are the same, but this point here, the C value, F prime of C, does not exist because it's a sharp turn. Okay, so it's not differentiable, so this is where one way the theorem could break down. Okay, so it's very important that you have all 3 of these conditions satisfied in order to be able to conclude that there is such a C. Okay, now we can use Rolle's theorem in many ways, but in one way, in combination with the intermediate value theorem, which you may have forgotten. But basically it says if the function's continuous, maybe I should write this. Let's write it in blue. Okay, so f of x continuous on a to b, then for any k value where k is between, I'm going to say f of a is smaller. Okay, so wherever k is between the f of a and f of b. Okay, so for any value that's between them, there is a c between, let me just write this a bit better. There is a c that's between a and b, where the function is equal to k. So f of c equals k. So you can pick any y value in between your two y values, and there's definitely an x value that hits it. Okay, so that's the idea behind the intermediate value theorem. So just to remind you, I mean, we saw that in chapter 1. So if we combine these, we can show that, say, these two functions have exactly one intersection point. Okay, so what I'm going to do to show this is I'm going to make a new equation, a new function. Okay, so let's let h of x be, it doesn't really matter, so let's do f of x minus g of x. So it's going to be cos of x minus 2x. Okay, so then if f and g intersect exactly when h of x is equal to 0. Okay, because that means that f of x equals g of x. So we're going to use the intermediate value theorem to show that there is at least one place where that happens. So if I do h of, say, 0, then I get cos of 0 is 1, okay, minus 2 times 0. Maybe I should write that. Okay, so cos of 0 minus 2 times 0, so that's going to be 1 minus 2 times 0, so 0. So that's going to be 1. And if I do, say, h of pi by 2, then I have cos of pi by 2 minus 2 times pi by 2. So I get cos of pi by 2 is 0. So I get 0 minus pi, so negative pi. Okay, so I can see, maybe I'll just write, so h of x, this function's continuous, this function is also continuous, so h of x is continuous everywhere. Okay, and k, if I take k equals 0, it's between h of pi by 2, my 0, and h of 0. Okay, so that means, so by the intermediate value theorem, which I'm going to call IVT, we know there is at least one C where C is between 0 and pi by 2, where h of c equals 0. Okay, so that was our k value. So the intermediate value theorem ensures that there's at least one x value, we're calling it c, where we hit this this y value. Okay, so that's this, but we're not quite done. So this gives us at least one solution, okay, but we actually wanted exactly one solution. So I want to show that there is not more than one solution. Okay, so we know there's one, and it happens to be between 0 and pi by 2 is where it occurs. We want to show, still need to show that there's only one, so that there is not more than one. Okay, and this is where Rolle's theorem comes in. So let's suppose there are two intersection points. Okay, let's say at C1 and C2. Okay, we don't know where they are, it doesn't matter. So let's say that there's two. So our function's continuous. Okay, so if there's two intersection points, that means that h of C1 is going to be equal to h of C2. Okay, they're both going to be 0, in fact. Okay, so if there are two, if we look up at Rolle's theorem, okay, so our h of x is this function here. Okay, it's definitely continuous on the interval between C1 and C2 because it's continuous everywhere. Okay, it's also definitely differentiable on the open interval from C1 to C2 because it's differentiable everywhere. And the y values at C1 and C2 are the same. They're both 0. So that means that there has to be a c value between C1 and C2 so that the derivative is 0 at C. Okay, so I'm just going to write here a little bit of what I just said. So I'm just going to write Rolle's theorem applies, okay, since h of x is continuous and differentiable everywhere, so definitely between C1 and C2, and h of C1 is equal to h of C2. Oops, C2. Okay, they're both 0. So that means there must be a C with, I'm going to say C1 is the smaller one, okay, but it doesn't really matter. So C between C1 and C2, and h prime of C equal to 0. Okay, so this is what's going to be the issue. So if I take the derivative of h, so it's cosine x minus 2x, so it's going to be negative sine x minus 2, right? That's the derivative. So h prime of c equals to 0 means that I have to have negative sine of c minus 2 equals 0. So if I rearrange this, this means that sine of c has to equal negative 2 for some c value in between these two C1 and C2s. Okay, there's a problem here. Okay, sine of c, it can be at least, the lowest it can be is negative 1, and the biggest it can be is not 2, it's 1. Okay, so sine is always stuck. Sine and cos both are stuck between negative 1 and 1. So there's no way that sine of c can be equal to negative 2. Okay, this is not possible, which means our assumption that there was h of C1 is equal to h of C2, that both there's two places where it's 0, is not possible. So now we can conclude there cannot be more than one solution. Okay, so I'm running out of room here, but if there's at least one solution and there can't be more than one solution, there has to be exactly one solution. So now let's increase to the mean value theorem. So all you do for that is basically rotate the picture for Rolle's theorem slightly. Okay, so we have similar conditions. Okay, so a and b are real numbers with a less than b. Okay, so they're just two different numbers. Your function is continuous on the closed interval from a to b, and differentiable on the open interval from a to b. Then what the mean value theorem says is that the instantaneous, there's a point c, okay, in the interval, where the instantaneous rate of change at c equals the average rate of change on the interval. Okay, so that's what it says. So the picture, what it looks like. So notice here I don't need that f of a and f of b are the same. Okay, so I go from a to b, and maybe they're different. Okay, so maybe they look like that, and our function looks something like this. Okay, so again, now I have, oops, this isn't very straight. So I have the line connecting them, so the slope here of this part is equal to f of b minus f of a over b minus a. Okay, so what the mean value theorem says is that there's some point c, I think it's around here, okay, where the slope of the tangent line is parallel. So same slope. Okay, that's what it says. And again, as before, it guarantees at least one place. There could be more places. Okay, but basically it's the same picture as Rolle's theorem, but tilted. Okay, so instead of needing a zero slope, I just need the slope to be equal to the average rate of change. So let's just use this in an example, and then we'll stop. So suppose a drone is used to patrol a highway and takes a picture of a yellow Mini 50 kilometers from a town. Okay, 30 minutes later, another drone catches the same Mini arriving in the town. Okay, so it traveled 50 kilometers in that 30-minute span. If the speed limit on that stretch of highway is 80 kilometers per hour, should the driver get a ticket for speeding? Okay, this is actually how they patrol the highways. So they're using the mean value theorem. So our function is, so let's say our f of x is the position of the car. Okay, and now driving, we're going to assume, okay, so that they drive continuously. Assume drive continuously in a differentiable way. So drive continuously and differentiable. Okay, so when you're driving, nothing weird happens, essentially. Okay, so we're assuming that so that it satisfies the condition. Okay, so then the mean value theorem implies that between, or maybe I should say at some point, between when the two pictures are taken, okay, so let's say that's t equals 0, so times 0, and t equals, now I want it in per hour, so instead of writing 30 minutes, I'm going to write half an hour later. Okay, so at some point between the time when the two pictures are taken, we must have, okay, f prime of c equal to the average rate of change on the interval from 0 to 1/2. Okay, so what that is it's going to be the distance traveled over the time that it took. So the change in distance over change in time. Okay, so that means that there's a c with f prime of c equal to, so we went 50 kilometers and they did that in half an hour. Okay, so that means that f prime of c is 100 kilometers per hour. Okay, so at some point between the two pictures, the Mini was traveling 100 kilometers per hour. Okay, so without actually seeing it happen, we know that it must have happened at some point. Okay, maybe at many points, but at some point it has to be that. And since the speed limit was 80 kilometers per hour, they should get a ticket. So they were speeding at some point. Okay, so that's one way in which you can use the mean value theorem.